these are the notes on force and Newton, meaning Sir Isaac Newton. So follow along with your Cornell notes. If you need to pause the video as we go through so you can finish the notes for each slide, please do so and take your time and go back and check your answers and check through, because I will be checking the summary at the end. So let's get started. So first thing is, what is force? Well, first thing is, a force is a push or a pull. You can see in the two diagrams, or the two images right here, we have the finger is exerting a force on the button, and the boy is exerting a force on his sister. A lot of times they'll use the this word exerting, and exerting means to put forth, to give a force, a push or a pull. So you can have a push or a pull as a force, and the word exerting just means to apply that force. How do you describe forces is the next one, and forces are described by direction and strength. A lot of times it will tell you that something's going up or down or backward or forward, north, south, east, west. That would be the direction. And they also use these things called vectors. The arrows, the larger the arrow is, the more force that's being applied. So if you have two arrows that you're comparing and it's asking about which one is the stronger force, it's going to be the one with the larger vector, the larger arrow. So they're described by the direction and also by the strength. How is a force measured? Forces are measured in the SI unit. Remember, SI means Systems International. Also, we call it the metric system. And this unit is called newtons, named after Sir Isaac Newton, but it's measured in newtons. You can also see that 1 Newton is about the force it takes to lift a small lemon. So not a whole lot of force there. So think about the force that you would apply to lift this lemon up, and that's the amount of force of 1 Newton. What is a net force? You can see this girl catching the light bulbs in the net. A net force is all of the force acting upon an object after being added or subtracted. That's what's known as the net force. So we'll see that different forces can be added to objects. So you always have gravity pulling down on objects that are on Earth. You also have friction that we will see as well in a couple other slides. But all of the force acting on an object is called the net force. How are forces combined? So talking about, if we go back to right here, talking about the net force, we said after being added or subtracted is known as the net force. If we come here, we're looking at how are forces combined, and this is exactly what we're talking about here. Forces are moving in the same direction, so they're both acting on the same object. They're going to become stronger. So you're going to add those forces together, and they're going to act like positive numbers. So forces, again, moving in the same direction. That's like your car stuck in the mud, and you're pushing on the back of the car, and somebody comes along to help you. They're going to push in the same direction as you, so you're adding your forces together. They're working in the same direction. So when you're looking at numbers, again, they act like positive numbers. You're going to add them together. When the forces are moving in opposite directions, they're opposing each other. They become weaker, so you're going to subtract those forces. So they act like a positive and a negative number working together. How are forces added? So you can see here I've got 5 problems written down for you. I just kept the numbers very, very simple. So if we look here, we got 5N, and remember N stands for Newton. So 5N and 5N. Then we have to know what direction they're going. So two of them going to the right. So 5 newtons to the right added to another 5 newtons to the right is going to give you, you're going to add those together. So we're going to get 10 newtons to the right. Notice the vector arrow for the 10 newtons is longer than the vector arrow for each 5 newton. 3 newtons and 6 newtons. Again, we need to know the direction that we're talking about. Again, the same direction. So if they're going the same direction, we have to add the numbers together. So we'll end up with 9 newtons to the right. Now we have 5 newtons and 10 newtons. So in this case, our directions change. So we have 5 newtons going towards the right added to 10 newtons going to the left. This might be something like an arm wrestling competition. Somebody's pushing with 5 newtons to the right, the other person is pushing with 10 newtons to the left. So who is going to win this arm wrestling competition? It's going to be this guy here, this 10 newton guy. But when you have to tell me what the net force is, you have to tell me by how much he's going to be winning. So he really is only going to win by 5 newtons. So our net force acting on those objects are 5 newtons to the right, or sorry, 5 newtons to the left. Now this one here, we have 5 newtons to the right and 5 newtons to the left. Here's something different that happens. When these two things happen and they're going in opposite directions and they're the same, again, one acts like a positive, one acts like a negative, so you're going to subtract those and you're going to end up with 0. So whenever you have this number of 0, you have a balanced force. So we'll talk about what that means in just a little bit. So it's a 0 newtons of force. So that this object is not going to end up moving in any direction. Then you have 7 newtons to the right and 3 newtons to the left. Opposite directions means that you're going to subtract the number. So we're going to end up with 4 newtons, and it's going to be to the right. So now we just kind of talked about balanced and unbalanced forces. So unbalanced forces, what really are they? They're forces that change the motion of an object. So anytime you have an unbalanced force acting on an object, you have a change of motion of an object. So the net force is not equal to 0. It's equal to anything other than 0. It can be equal to 1, it can be equal to 200, it can be equal to 539. It just doesn't matter as long as it's not equal to 0. So it's not equal to 0. There's 4 ways that you can change the motion of an object. First, you can cause an unbalanced force can cause an object to start moving. So to start motion, that's one way. The second way is to stop motion. So you have an object that's moving and then you apply a force to it to make it stop moving. You can also change the speed. So anytime that you have a force applied to an object to make it change the speed, that can be speeding up or slowing down, you have an unbalanced force acting upon that object. And the fourth way is for it to change direction. So even though something is going the same speed, and if it changes the direction, it's being acted upon by an unbalanced force. So what are balanced forces? The opposite of that. So balanced forces are forces that do not change an object's motion. So that means in this case that the net force is equal to 0. Now before, remember, unbalanced forces were not equal to 0. So they could be any number but 0. With balanced forces, the net force is always equal to 0. So it can only be equal to 0 newtons. So from examples are, there's no change in the object's current motion. So let's say you have a plane that's flying at 500 miles per hour going eastward. And that plane is going to continue to go 500 miles per hour eastward. It's not changing direction, it's not speeding up, it's not slowing down. That plane is under the effect of balanced forces. The object remains still is another way that forces are balanced on that object, that it's not going to start moving, it's just going to stay stopped. So those are the 2 ways that objects can remain under balanced forces. So we have these same problems that we just looked at. So it says, what does the net force tell us? So we have those problems. So we have 10 newtons to the right, 9 newtons to the right, 5 newtons to the left, 0, remember, and then 4 newtons to the right. So looking at the net force, you're going to be able to tell, is there motion or change in motion or not? So looking at these, you can tell that this one is unbalanced. So because that object that these 2 newtons, these 2 5 newton and 5 newtons are applied to, is going to end up going to the right with 10 newtons of force because it's been applied. Same thing for this one. This object is going to move to the right. This object is going to move to the left. This object is balanced. So this object is not going to move at all because it has a net force of 0 right there. So that's the difference. And this object, it will eventually move to the right as well. So that brings us to friction. Friction is a force when 2 surfaces rub together. And there are 2 things that the strength of friction depends upon. First thing is how hard the surfaces are pushing together. So if things are pushing together really, really hard, they're going to have a whole lot more friction than something that's just lightly scraping against each other. The second thing is the types of surfaces. If you have a really rough surface, it's going to exert more friction force than a smooth surface. So if you want to reduce friction, you obviously want to not make those two objects press together too hard, and then you also want to have the surface to be a lot slicker or smoother surface. So the thing about friction is, it says in what direction does friction act, and you can see in this diagram that's labeled up here, you've got the friction forces are going backward and the direction of motion is going forward. And that doesn't always have to be the case. Friction force doesn't always go backward. It always is going to go in the opposite direction of the motion. So let's say someone's jumping out of an airplane and they're going down, and friction is actually going to be going up, so it'd be opposing the motion that it's going. If something was going backward, then the friction would actually be going forward. So it'd be the opposite of whatever the motion of the object is. It's going to oppose motion every time. So can all surfaces have friction? Yes, absolutely. All surfaces have a texture. Even sometimes when we think it is smooth, microscopically it's really very bumpy. So we have different levels of friction, but all surfaces, including really, really smooth surfaces, have some type of friction on some level. Maybe very, very little, but they have friction. And this is a microscopic picture right here. I think this is a piece of paper under a microscope. So you can see a piece of paper like notebook paper. You can feel it. It feels very smooth. You wouldn't think, oh, that's rough and it has a lot of friction. But if you put it under a microscope, you can see all the fibers that are intertwined here. So there is some amount of friction. All right, so the four types of friction. You have static friction that acts on objects that are not moving. That's going to keep an object in place. If you've ever noticed you tried to move furniture that's sat in place for a while, it is under the effect of static friction. So you have to give it kind of an extra push to get it to moving. And then once it starts moving and sliding, it changes to the second one, which is sliding friction. So two solid surfaces are going to slide over each other. So that's when it's undergoing sliding friction, when you have two surfaces that are solids sliding across. Then you have rolling friction when objects are going to roll across the surface. So like roller skates or a golf ball rolling on a green, or a bowling ball rolling down the lane, something like that. And then you have fluid friction, and that means that a solid is in a fluid. So remember, a fluid, back from when we were talking about fluids, when was that? We were talking about that with energy. A fluid can be air or it can be water, because even gases, they're something that flow. So if gases flow, they can be considered a fluid. So if you have a plane going through the air, you have fluid friction. If you have a boat going through water, fluid friction. So those are the four types of friction right here. There's some pictures. So this surfer has fluid friction, obviously going through the ocean, the surfboard to the ocean. There's different types of friction in this picture, and then there's a different type of friction here. You have another type of fluid friction as the car moves through the air. All right, and here's some types of friction. So this little lady, she's got, I guess, she has rolling friction here. He's sliding friction. Match would be sliding friction. The shark would have fluid friction. Then over here you have different types of friction as well. So you have some sliding, rolling. Basketball players sliding, baseball players sliding, roller skates are rolling friction. So just some images to think about. So how do you reduce friction? What if you have too much friction? You have to add oil between the parts of a machine. Machines really use a lot of energy to try to overcome friction. That's what makes machines more efficient or less efficient, is really based on the amount of friction that they have. So you can add oil between those parts of the machines, and those parts of the machines will then change from sliding friction, if they're scraping against each other, two solid surfaces, to floating friction, which again, there's still friction there because the two surfaces are touching, but if you put the oil in between there, then the surfaces aren't really touching, they're floating kind of in that fluid between. So now we're moving right on into going back to those forces, and we're looking at unbalanced forces that change an object's motion on Earth. So we have two forces that we're constantly battling on Earth. Number one's gravity, because gravity is going to constantly pull us towards the center of the Earth and all objects around us towards the center of the Earth. So we're constantly battling gravity. And then friction. And friction, sometimes that's good and sometimes that's bad, just depending on the situation. A skier would like to not have a whole lot of friction so that they can gain some speed. And then somebody walking down a hill, if you're not prepared, you definitely want to have friction and grip on the bottom of your shoes so you won't fall. So depending on the circumstances, depends if you want friction or not. So those are two types of forces that are always in effect on Earth. Now here's Sir Isaac Newton, and we're going to be studying. Newton did a lot of work studying motion, and he is noted with some laws. There's 3 laws, and we're actually just going to go through the first 2 laws today and work on those for a little bit, and then we'll add the 3rd one later. But this is Sir Isaac Newton and his 2 laws. So his first law of motion states that an object at rest will stay at rest, and an object in motion maintains its velocity. So sometimes you'll hear that say an object in motion will stay in motion, which is true, but you also have to be a little bit more specific because we're in high school. It will maintain its velocity. That means it's going to keep, remember velocity is, let's go back, a velocity is, velocity is speed and direction. So it's going to keep the same speed and it's going to keep the same direction. So let's read that again. It states that an object at rest will stay at rest. So if it's not moving, it's not going to move. It's going to be balanced. An object in motion maintains its velocity. So that means an object in motion will keep its speed and direction. So it won't change speed and it won't change direction unless, so remember that object at rest should stay at rest. Object in motion should maintain its motion or its velocity unless something happens, unless it experiences a net force. Now remember back from those slides that we just talked about, what is a net force? A net force is going to be a number, right? A number of a force acting on an object. So an object is going to be moving to the right or left, or up or down, or forward or backward. So if a net force is acting on that object, it will change. But that first law says an object at rest will stay at rest. An object in motion maintains its velocity unless it experiences a net force. So that means that it has to be a balanced force. An object at rest stays at rest because it's balanced. It has 0 net force. An object in motion maintains its velocity because it has 0 net force. So it's balanced is what that's saying. Now if it experiences a net force, then it will change. So here's just some information. This was copied from the Georgia Driver's License Manual, talking about safety belts. And safety belts are really applied to the first law of motion because they are there for our safety. They're needed because they're the most effective occupant protection in all types of vehicle crashes. It helps you keep control of the vehicle. It helps keep your head from striking the dash or the windshield. It helps keep people in the vehicle from hitting each other. It helps spread the crash force along stronger parts of the body. It helps protect you from injury, and it helps keep you from being ejected from the vehicle. So, because when you're in a car and you're going a certain speed, your body is also going that certain speed. So if that car were to change speed abruptly, your body doesn't want to. It wants to keep going because of its, what we call its inertia. And that is directly related to Newton's first law of motion. So those seat belts are really important, and that's why. It's because that law of motion is a law. You can't get away from it. It's going to happen. So again, what is the first law called? It's called the law of inertia. And there's that word right there. It's spelled a little bit differently than what you think, but that's the law of inertia. Do different objects have different inertia? Yes. The inertia of an object is directly dependent on an object's mass. So how does mass affect inertia? If an object has more mass, it has more inertia. This means that the object is harder to start or to stop moving. So something that's really, really large with a whole lot of mass is really, really hard to start moving. So think about friction. It has more static friction as well. So it's harder to start moving. And then again, once you get it started, it's harder to stop moving, especially if you look at the cars here. Think about those two cars. If we had to push the Volkswagen Beetle, we could probably do that if we put it in neutral pretty easily with a couple people. The semi-truck, not so much. The semi-truck has more inertia. It has more mass. The same thing's true as if once these are both going, if they're both going at 55 miles an hour, it's going to be a lot easier to stop the Volkswagen Beetlebug than it is going to be to stop the semi because of its inertia. So if an object has less mass, the opposite is true. There, it has less inertia. So it's the same thing. It's a directly proportional relationship. More mass, more inertia. Less mass, less inertia. And in this class, I know we've talked about relationships and how things relate to each other. And that's what we really have to look at. It's not just defining terms. It's understanding how they work together and how one thing affects another. So the opposite is true here. This means that an object is easier to start and it's easier to stop moving as well. So if I look at these two, the Beetlebug has less inertia because it has less mass. It's easier to start, it's easier to stop. The semi-truck has more inertia, it has more mass, it's harder to start moving, and it's also harder to stop moving once you get it started. So now we're to Newton's second law. And Newton's second law states that the acceleration of an object depends on the mass of the object and the net force acting upon it. So it states that the acceleration of an object depends on the mass of the object and the net force acting upon it. So here we have a man pushing the car going forward. So the mass of the car and his force applied is going to be able to tell us how much this car is going to accelerate forward. And there is a mathematical equation that we're going to put on here in just a second. So here it is. How is Newton's second law calculated? Well, here we go. Force is equal to the mass times its acceleration. It's abbreviated F equals ma. Force is equal to the mass times the acceleration. So let's think about what that means. The mass is 55 kilograms. The acceleration is 2.0 meters per second squared. So in order to know the force that I would need to move 55 kilograms and get it to accelerate 2 meters per second squared, then I need to look at multiplying those two together. So how much force would I need? Well, 55 times 2 is going to give me 110. So 110, and that's going to be kilograms per meter per second squared. And I can also rewrite that whole unit. That's what's called a Newton. So that's called 110 newtons. Example 2, acceleration is 3 meters per second squared. It's a mass of 1,000 kilograms. So how much force do I need to apply to move a mass of 1,000 kilograms 3 meters per second squared? Again, you multiply those two together because force is equal to mass times acceleration. Substitute what I'm told. So 1,000 times 3, I get 3,000 kilograms per meter per second squared, which is also written as 3,000 newtons. So again, that unit kilogram per meter per second squared is defined as a Newton. Third example, the mass is 25 kilograms and its acceleration is 14 meters per second squared. So again, force is equal to mass times acceleration. So force is equal to 25 kilograms times 14 meters per second squared. So that is going to end up being force is equal to 350 kilograms per meter per second squared, or 350 newtons. So there's two things that you can do to increase the acceleration of an object, and let's think about this relationship. If I was pulling this wagon or pushing this wagon of kids, there's two things I can do to make them go faster. The first thing is I can decrease the mass. So that means I can take a kid out. right? And pull it the same way with the same amount of force. So I take one of those kids out and I start pulling that wagon with the same amount of force. It's going to go faster because it just is. And the second thing I can do is I can increase the force. I can keep both kids in it and I can just pull it harder. So that's true for anything that you're talking about. How do you increase the acceleration of an object? You can decrease the mass that you have to accelerate, right? Or you can increase the force that's applied. So think about that. If I have a bowling ball compared to a baseball and I want to throw them both, and if I want to accelerate them both at the same speed, I have to use two different forces because they're two different masses. Obviously, to get the baseball to go at a speed of 10 miles an hour, it's going to take a lot less force for me than it's going to be to apply to the bowling ball, to get the bowling ball to accelerate to 10 miles per hour. So if we think about applying it to those sorts of things, I always think about having a big grocery cart full of stuff. And if you think about having a grocery cart full of stuff, if it's really, really full, if you have waters and Gatorades and all kinds of heavy stuff in your cart, you really, really have to put a lot of acceleration. You have to push it to get it to go. And if you have a really light cart, you can just tap it and it'll go down the aisle. So those are just some practical applications of force is equal to mass times acceleration, which you do every single day. All right, we're going to say that comprehension check for tomorrow. That's right here. So here's what I need you to do. I need you to look at your Cornell notes, and I need you to look at the summary part, and you need to go back through. So let's get out of this and let's go to our, let me show you your summary part. So in your Cornell notes, which you have a copy of in front of you, on this last part, all of this should be filled in. So if you need to go back in the video, go back, pause it as you need to, make sure all of this is completed. And then the very last thing that we need to do is to summarize. And when you get this summary done right here, this is what you need to do. You're going to write in complete sentences. It won't take too many. 5 sentences would be sufficient if you can do that in there. You may need to take more. If you need more, just get out a sheet of notebook paper. That's no problem at all. If you prefer lines, you can do the whole thing on a sheet of notebook paper. But your summary, because what we've talked about in these notes, need to describe what forces are and how they act. So that's the first thing I'm going to be looking for. Did you tell me what forces are and how they act? Like, are they balanced? Are they unbalanced forces? I need you to summarize specifically friction. We'll look at gravity later on this week. But summarize friction. So that means the 4 types of friction. And what is friction? And what are the 2 factors that increase friction? So that needs to go in your summary. And then the third part of this that I'm looking for is that you're summarizing Newton's first and second laws of motion. So remember that law of inertia that we talked about. And remember the force, mass, and acceleration. So those are the things when you bring your summary to me, I'm looking to see. Did you tell me what a force is? Did you tell me how they act on objects? Did you summarize friction and the 4 types? Did you tell me Newton's first law and its second law in your own words? And that's what I'm looking for. And I do want to read your summaries when you're finished. If you do not finish your summary in class today, you can finish it for homework, and you can bring it back to me tomorrow, and I'll check that first thing before we go on to some guided practice. This week, what we're going to be doing is focusing more on gathering our information, and then we'll be ready to apply all of this next week to some labs. So, when you have your summary done, come to me and turn it in.